So today we're going to talk about direct digital manufacturing, going right from a 3D computer model to a physical part. So before we get started on the content, just a little bit about my company, NeoMetrix. So we get started in 2003, and we are an engineering service provider as well as an equipment reseller for 3D scanning and 3D printing technology. So here we have a list of the vendors that we currently represent, as well as a listing of our products and services. All right, so before we talk about direct digital manufacturing, we'll talk a little bit first about the traditional process where engineering does a design and then typically sends a drawing to manufacturing, parts fabricated, and then it goes to quality control for inspection to ensure that the final part actually matches the original design. So 2D engineering drawings can be very complicated. So I searched the internet just looking for drawings, found one that looked complex enough to make my point. So as you can see, for a complex part, there are a lot of dimensions that are required to fully define that. So generating these types of drawings, especially in the days before computer-aided design, was very, very time consuming. You need a very skilled draftsman or engineer to generate this kind of data. And it still may be difficult to fully define a part using these traditional methods. And you may end up designing a part that is not manufacturable. Then that drawing would go over to the fabrication shop where you had people running manual machines, and they would have to interpret those drawings and manually generate all those features on those parts. Again, you need very, very skilled technicians and operators to do this type of work. Very time consuming, and ultimately your part quality depended upon the skill level of the man or the person who was operating those machines. Finally, that part, however complex, would end up going to quality control, and especially many years ago, the tools for inspection were really limited. You had calipers, height gauges for larger parts, tape measures. So really, only 1 and 2D dimensions were able to be checked using these types of tools. So you could have a part that would it might be impossible to measure with these tools, or you have a limited inspection, so you have a part that passes inspection, but may not necessarily work. So there are a lot of flaws in the traditional process. But again, before 3D technology, this was really what was available. So if we can compare the traditional method we just talked about to a direct digital manufacturing workflow, engineering will then develop a 3D model either through traditional CAD, designing from scratch, or through 3D scanning. Send that 3D model directly to a 3D printer for additive manufacturing, and then again can use 3D scanning technology to scan that final fabricated part and compare back to the original design. There are direct digital manufacturing examples all around us. Right? Anybody who's been to the movies, especially science fiction, superhero movies, a lot of the costumes and props all went right from a 3D design through a 3D printer, and now they're in the movies. Fashion, you're starting to see 3D printed shoes and dresses and things of that nature. Especially here in the Orlando area, we have a lot of theme parks, a lot of direct digital manufacturing and 3D printing in the theme parks, from character costumes to props that are on the attractions and things like that. Medical and dental, very good example of direct digital manufacturing. You can go to the dentist today if you need a crown. They'll scan your tooth, have a 3D printer right in the office, and fabricate a new crown just for you. Prosthetics, another area where this technology is used a lot. The technology really fits when you need low volume, custom parts for a very specific application. Medical, perfect example of that. Here also you have a 3D printed example of a skull plate. If you, unfortunately, part of your skull is missing, you don't want one off the shelf, right? You want one designed especially for you. So these are all great applications for this technology. So about 30 years ago, people were moving, engineering design companies were moving from drafting boards and 2D CAD to 3D CAD. This is really where this process started in its infancy, where now professional 3D CAD systems like SolidWorks and Pro Engineer allow you to design your parts in 3D, and then you can, again, of course, go right to the 3D printer. A lot of professional 3D CAD systems available today, as well as alternative ones. There's a very large growing community of hobbyists using 3D printers, people running small shops out of their own house. Can't necessarily afford the professional level CAD, but there's a lot of low cost and actually free for hobbyists. Onshape is a product. It's a full online 3D CAD system, no cost to hobbyists, design in full 3D. Now, if you wanted to go from an existing part to create a 3D file, that's where we get into reverse engineering, creating those CAD files from 3D scans. So, not everybody's familiar with all the terms in the 3D scanning and reverse engineering world. So 3D scanning is, you rapidly capture geometry using some sort of optical device that will generate a cloud of points. So the data is millions and millions of data points that define that object in space. Take those points, start connecting the dots to create triangles, and that's how you get to a polygon mesh, which will typically save out as an STL file. Now that is something that can be tweaked a little bit, go right to the 3D printer, or use as a starting point to create a 3D CAD file. There are lots of different scanners available. So we're a representative for Creaform, so the handheld units up there, great all-purpose devices, for scanning things from, let's say, golf ball size up to small cars. For smaller, higher precision parts, we have tripod-mounted structured light scanners. For larger items, you can see there the optical tracker with a handheld scanner. So I like to say scanners are like screwdrivers. Not one tool is good for every application. So if you're looking to invest in a system, you probably want to find the one that covers about 80% of your application. Okay, choosing our path. Do I want to go right from scan to print, or do I want to go from scan to making a CAD file? That's really going to depend upon the types of parts that we're looking to reverse engineer. So if we start with things that are more free-form and organic, we can typically scan those in a couple positions, align those scans together, and then merge that data into a single STL file. And with a little bit of tweaking, some hole filling and smoothing, I've got a file that I can then send right to a 3D printer. If I have something more complex, where maybe there's a lot of line of sight issues, a lot of small features, I may not necessarily be able to go right from the scan to the printer. I might need to generate that 3D CAD file. So we have a workflow in a program, Geomagic, that we use, where we take the scan data, which is a mesh, and then we use that as a starting point and cut cross sections through it, and then build our geometry with sketches and things like that to come up with a final solid model. Now that's our perfect model, and then now we can send that right to the 3D printer. So here's a little bit about the Geomagic that we use. So this is one of the products that we can take the raw scan data, and we can either clean that up and tweak it, or we've got all the tools available to then generate that 3D solid model. All right, so now we've got our file, either our STL file from the scan or a CAD model that we created. We're ready to go to 3D printing, so let's talk a little bit about that. So the history of 3D printing starts way back in 1986. The first machine was called the Stereolithography system. Started with an open vat of resin, and the resin was cured with a laser, one layer at a time. Very complex, very expensive. You could do highly intricate parts, but the materials were pretty fragile. So really not for production applications, much more for prototyping. If we compare that to today, there is a wide array of different technologies. You've got FDM, FFF, SLA, DMLS, very, very wide range. So today we're primarily going to focus on the FDM technology, which is extruded plastics. Most of your printers out in the market today use this technology, and the products that we represent also use that technology. Okay, so choosing a printer or choosing a material really going to depend upon your application, right? What are the requirements for the material? How big are the parts? You know, how much money do I have to invest in the system? These are all things that we need to consider before we start 3D printing. So most FDM, or actually all FDM or FFF style printers use thermoplastics. So we have a plastic filament that's going to get extruded through a nozzle to build the parts up layer by layer. A lot of your entry-level systems and some of your higher-end ones use a material called PLA, which is it's a biopolymer. It's a low-temperature plastic. It's very easy to extrude, and it is inexpensive. It does not have the most robust material properties, but it's really good for parts where you don't have a lot of strength requirements. Next step up from that would be some of your engineered plastics. We get into stuff like ABS and ASA. So ABS has very good mechanical properties, higher tensile strength than a PLA, better impact resistance. So good for making end-use parts that need to be durable. ASA is very similar to ABS, but has better UV resistance. So if you're fabricating parts that need to be used outside, ASA is a good choice. If you have more demanding material requirements, then you can get into the higher performance thermoplastics like PEEK, PEC, and Ultim. These are a little bit more difficult to print because it requires a high temperature printer, and the materials are a little bit more finicky. But you've got much more robust parts that you'll fabricate, good temperature resistance, and very good chemical resistance. Some FDM printers can also use composite materials. So one of the claim to fame of Markforged printers is their Onyx material, which is it's a nylon, but it's infused with chopped carbon fibers. So we like to use the example of composite materials, talking like how concrete works. So you concrete, you add cement, but then it's also filled with some sort of aggregate. So that's a composite material. Similarly, the Onyx has a nylon base, but then it's got the chopped carbon fibers in there, which act like the aggregate does in concrete. The other thing that Markforged printers do that a lot of other printers don't is the ability to add continuous fiber reinforcement. So you get your base material, the Onyx, and then you can add continuous carbon fibers. So this is, again, using the concrete analogy. If we've got our concrete and then adding rebar adds that additional strength, that's exactly what we're doing with the continuous fiber reinforcement in the base Onyx part. All right, so we talked a little bit about printing. Now the parts, let's say our parts are printed, we want to check them and make sure they match the original design. We could go back to 3D scanning. One of the software tools that we use for inspection and comparison of our parts to CAD is the Geomagic ControlX. So this software product allows us to take a scan of the part and overlay it on the original design, either a full CAD model or an STL we got from scanning, and then do a comprehensive comparison. So the advantage in using scanning for inspection over using hand tools is that you can fully describe the part, right? If I use a pair of calipers, I can measure one feature at a time, and it's really only one-dimensional. Scanning, I can scan the entire object and then get this color map report by comparing it to my original CAD. So first step, we've got our CAD file. It's a gray object. We've got the scan data, which is the blue one. We align them together. Got a lot of different tools to do that. You can either do like a best fit alignment, or you can use specific geometric features on the part. This plane goes here, this hole goes there. So you've got a lot of flexibility as far as the alignment goes. Once it's aligned, then we can do a 3D comparison. That's that color map. We set a global tolerance. Everything that falls within that tolerance will be green. As things start moving out of tolerance, then they go red on the high side, blue on the low side. So you get a very quick graphical interpretation of the quality of the part we produce. Again, if you compare that to using hand tools, where I take my measurements and maybe I write them down on a piece of paper, it really doesn't show you a picture of what's going on with your part. Whereas these type of tools are very, very graphical. It can clearly tell you where your issues are, if you have any. If you had the requirement for doing geometric dimensioning and tolerancing, that's also available in ControlX and other inspection software products. So things like true position, flatness, parallelism, all that. Simply pick the appropriate function, and you can pull those right off the CAD file. Again, circling back to Markforged, they've actually integrated a scanner into the printers. So the industrial series printers from Markforged have that integrated scanner. They've got a new software product called Blacksmith, which actually scans the part as it's being printed. So when you're done, you'll get an analysis of how well your final part matched that original CAD. Then taking it a step further, it can adjust the model inside the program so that when it runs the next part, it'll more closely match the original design. So it iteratively improves the result of the print based upon the scan of the first iteration. All right, so that's our direct digital manufacturing process. Kind of wrapping it up, let's talk a little bit about where does this fit and where it doesn't fit. So where doesn't it fit? Very, very high volume parts. Right, so if I need millions of something, I probably want to go to more, like in plastics, go more to an injection molding sort of process as opposed to try to 3D print, because 3D printing as compared to molding is much slower. If I only need a few parts, that printing makes sense. If I need millions, then it makes more sense to invest in a tool. Or if I have very simple geometry, here's an example of a pipe, right? Why would I want a 3D printed pipe? I'd probably go to Home Depot and buy one. Sheet metal, like folded sheet metal parts for enclosures and things like that, again, not really a good fit for this kind of process. Or if you have very stringent material requirements, I like the example of aircraft structures. Those are very, very heavily regulated by the FAA, and materials and fabrication processes all have to be certified. So again, the direct digital, not really the best fit for that. So where does it fit? Low volume. If I only need one or two of something, or a handful of parts, very good example, or very good candidate for 3D printing. If I have something that's really complex and cannot be manufactured any other way, not machinable, that's a good example. Custom, again, I'm talking about the medical, or maybe items that have a long lead time. So here we have an example of a holding fixture, the black part, Markforged print, holding a part. If it took me 3 or 4 weeks to get that from a machine shop, not a lot of real structural requirements, I could print that, put it on the printer tonight, and have that fixture available for me tomorrow. So those are all really good examples of where direct digital manufacturing fits. All right, coming to the end, I wanted to extend an invitation to everyone to attend we have an upcoming open house at our facility in Lake Mary on the 27th, where we'll be talking about all of this stuff and have all of our scanners and printers available if it's something that you'd like to experience. We're also exhibiting here at the show today in booth 203. We've got a scanner there, we've got printers, printed parts. If you wanted to stop by, we'd be happy to chat with you. All right. Well, thank you everybody for coming. Again, if you wanted to stop by and chat a little bit more, we're in booth 203. Yeah. And we do have some invitations there for our open house if you're interested in attending that as well. So thank you very much.